Okay, the next section is on composite functions. If you understand function notation, it's very easy to form a composite function. So, we're going to assume that we understand function notation. It was done last week. Everybody's been through the exercise. If f of x equals x squared and g of x equals 2 to the x, then the composite function, which we designate f circle g, has formula that you get by substituting into the form f of g of x. Okay? So f of g of x is the value of the composite function at x. So we could say f of g of x at x so it's the f circle g function evaluated at x has value f of g of x. Okay, well, it's easy to write down the formula for a composite function if you know the formulas for the f and the g functions. F of g of x, well, f of x is x squared, so we replaced x by g of x. When we substitute g of x for x, we get g of x squared. And g of x squared is what? Well, g of x is 2 to the x, so that's 2 to the x squared. And then if you know the laws of exponents, then you really need to know the laws of exponents. 2 to the x squared is 2 to the 2x. I'm not going to explain that. You need to know the laws of exponents. Okay. Now what about g of f of x? Well, g of f of x means you've replaced x in the definition of g of x by f of x. So you replace this x by f of x, you're going to get 2 to the f of x, which is what I've written here. And then, of course, since f of x is x squared, this is 2 raised to the x squared. Now, we see in what we're doing today, what we did with the quiz where we transformed the graph by shifting it right or left or up or down and moving it closer or further from an axis. If we apply transformations of that nature to the basic functions, we get a whole lot of the functions that we study in pre-calculus and calculus and functions that we apply out in the real world. Another way of generating functions from the basic functions is just what I've done here. We do composites. Okay, one of the most important functions in mathematics is very closely related to what we get if f of x is 2 to the x, g of x is negative 1/2 x squared. The f of g of x function then is, well, f of g of x would be, replacing x by g of x, it would be 2 to the g of x, and g of x is negative 1/2 x squared, so I haven't written the intermediate step, but that's what we get for f of g of x. And we can construct this graph, and you'll see in your assignment for Thursday just how you can construct a graph from a table or graph of each of these functions, each of the two functions. In other words, how you can construct a composite from the graphs of the two functions or from the table for the two functions. Okay? That function has this shape. It's your standard bell-shaped curve, which is extraordinarily important in applications. So, there we have a couple of examples. Now we want to go on and talk about domains of composite functions. So let's do a couple of examples. And I think I have another board before we do this one. Actually, got to bring this one back. I addressed that here. Then I got off of talking about this and didn't come up here. Sorry. So f of g of x, for f of x is 2 to the x, g of x is 1 over x. Well, f of g of x is then 2 to the 1 over x. You can do the steps. 2 to the 1 over x is a great function, except, you can't substitute every possible x value in 2 to the 1 over x, because the first thing you have to do after substituting is divide x into 1. And you can't divide 0 into 1. You can't divide by 0. So x can't be 0. Now, any other x will give you a real number, but 0 won't. Well, any other x gives you a real number, and you can always raise 2 to any power if the power is a real number. This means then that the domain of this function is negative infinity, 0, union 0, infinity. You have to exclude 0. Now, the reason you exclude 0 is because your g of x function, we call this the inner function. If you're given an x, you've got to plug it into g of x before it goes into x. In other words, you've got to do the 1 over x before you raise the function 2 to that power. Okay? That's one way your domain can be restricted. Another way your domain can be restricted is if the value of g of x doesn't work when you plug it into f of x. That restricts the domain. So as an example, f of x is 1 over x, g of x is x minus 3. F of g of x is going to be, well, replace x by g of x, you get 1 over g of x. That's 1 over x minus 3. Now you know that this denominator is not allowed to be 0, because then you're dividing by 0 again. The denominator can't be 0, so x can't be 3, because very obviously, if x is equal to 3, your denominator is 0. Here then, your domain is restricted not by g of x, you can plug any number at all into g of x, but by what you get when you plug 3 in for g of x, because you can't do 1 over, because plug in 3 to g of x, you get 0, and 0 won't go into the function f of x. 0 can't be used in the function f of x. So, your domain would then be negative infinity, 3, union 3, infinity. Okay, f of g of x then, for f of x equals 2 to the x, g of x equals 1 over x. It's undefined for x equals 0, as we saw previously. And we say that f of g of x can't be defined if g of x can't be defined. And f of g of x can't be defined at values of x at values of x for which g of x isn't in the domain of f of x. Okay, that's this example. So there are two ways the domain can be restricted. The values of g of x in the domain have to lead to numbers that work in the f of x function. And you can't use values of x that make g of x undefined, which could happen, for example, in this case.